Chapter 5, Thermochemistry. We are going to start focusing on thermodynamics, and we are really going to start getting into material that we haven't covered last year in regular chemistry. So this is kind of the beginning of the advanced chemistry portion. We are getting brand new information in regards to chemistry. And we start with a topic which is not necessarily the most fun, but we'll go through it and you'll kind of understand it as we go. So thermochemistry, what does thermochemistry deal with? We are dealing with energy. Now remember, what is energy? Energy is essentially the ability to do work or is a transfer of heat. So we have two different definitions there, and both of these are physics definitions. All right, so we're going to dabble a little bit with some physics in thermochemistry, but the ability to do work or transfer heat. So what's the difference between doing work or transferring heat? Energy used to cause an object that has a mass to move is called work. So anytime we're moving an object, it's called work. Anytime we cause the temperature of an object to rise or fall, it's called temperature. Now, what are other different types of energy that we may have studied or that you can list of? There's a handful of ones that you probably could list. There's kinetic energy, Ke. There's potential energy, Pe. There's mechanical energy. There's chemical energy. There's electrical energy. There's nuclear energy. So those are just a couple types of the different types of energy that you can have. So we're going to talk about energy, what causes energy, where do we get energy in atoms, and where do we get energy in chemical systems. When we start talking about atoms and the kinetic energy of moving objects, we're going to use the equation for kinetic energy. And they go EK, I can prefer KE, it's what you've had in the past. Kinetic energy is equal to 1/2 mv squared. And remember, kinetic energy is equal to 1/2 mv squared, where m equals your mass in kilograms. And your velocity is, v is velocity, and that's in meters per second typically. So that is your units for kinetic energy. You've studied kinetic energy in the past in 9th grade physical science, and if you're in physics, you'll get more with kinetic energy as we go. What is potential energy then? Kinetic energy was Ke. Potential energy obviously is Pe. Now there's two different types of potential energy really. You can have kind of the electrostatic potential energy that molecules have. And that equation is a constant. The potential energy that molecules have is equal to K times Q1 times Q2 over D. Now, what do each of those stand for? K is a constant. All right. K is a constant in that equation, which is equal to 9.0 times 10 to the negative 9th. Right. Q is the charge of the molecule. So if we're comparing two molecules, we're comparing the charge, and those charges are going to be in coulombs. And then D is the distance those molecules are apart. So that is when we're talking about electrostatic potential between two molecules. If we were just talking about general potential energy, remember potential energy is equal to mass times gravity times height. And that's kind of how you learned it in physical science in 9th grade. Remember, there is a distinguishing difference. We're talking about electrostatic potential down below and just general potential energy. Up top, m times g times h. The m represents mass, the g represents gravity, and h is the height above the ground that you are. Remember that g is 9.8 meters per second. That's the speed at which an object is accelerated due to Earth's gravitational field. So, two types of potential energy exist there. We have electrostatic on the bottom, and we have just general potential energy as a basic refresher on top. Now, when we talk about energy, the units for energy is a joule. And a joule is equal to 1 kilogram times meters squared over seconds squared. Now, 1 joule is also equal to, all right, it's also equal to 1 calorie is equal to 4.184 joules. Now, a lot of times you get caught up in the unit a calorie. Remember, what we eat is kilocalories, not actual calories. So what you eat, you're supposed to get 2,000 calories in your daily diet. That's actually 2,000 kilocalories. So the calorie is a unit of energy that we use for food. It used to be used for energy, but for the most part we see joule, but it is potential they may sneak in a calorie question. So when we talk about energy, there are 2 defining aspects that we need to talk about. We need to talk about the system and the surroundings, because those are the only 2 things which can give off energy. And remember, energy is defined in 2 ways. Work, by moving an object, or heat, by the rise in temperature. So those are the only 2 ways that we can do something on a system, create energy in a system, by creating work or by creating heat. And we can create that on the system or the surroundings. So let's go ahead and let's look at this. What is this system? The system includes molecules we want to study. So if we had a piston here, our system are all these molecules that we're studying. The surroundings is everything else. So the surroundings is the piston, the canister, the air on the outside. The system is air, the surroundings, everything else. So the system is what we want to study. The surroundings is everything else. So keep that in mind. So we just got done talking about energy, the basic units for energy, or the basic equations, kinetic and potential. But remember, kinetic energy was defined as the ability to either move an object a distance, do work, or a rise in heat for temperature. Well, work is equal to force times distance. So work is equal to force times distance. Since it's a unit of energy, it's measured in joules. Force typically is measured in newtons, and distance is typically, as always, as you can imagine, measured in meters. So force is newtons, distance is meters, work is equal to force times distance. Work, it can be positive or negative, and we'll talk about that in the next upcoming slides. So that is work. So that, remember, we can do work or we can do heat. And energy can also be transferred by heat. And remember, heat is the addition or a rise in temperature. So heat is a rise in temperature. One key law about, one key thing here to note about thermodynamics, heat flows from warmer objects to cooler objects. So heat flows warm to cold. So we have work and we have heat. Now what we're going to talk about the entire section here in thermodynamics is the transfer of these energies between systems and surroundings. Now if you look at the picture here, we have a very, very, very simple conversion of energy. All right, the bicyclist is on top of a hill. That means they are standing still at the top of a hill. That means at the top of the hill they have 0 kinetic energy and tons of potential energy. Right. What's going to happen the second they go down the hill, though? The second they start going down the hill, what's going to happen to their kinetic energy? It's going to start increasing. Why? Because they're moving, their velocity is increasing, and their potential energy is going to decrease because they are getting closer to the bottom of the hill, so they are losing their height. However, when they convert, the cool thing about this is since energy is always conserved, the amount of potential energy lost is the amount of kinetic energy gained in this system. Now, that's not taking into effect friction and other losses of heat along the way due to mechanical error and on the bicycle and everything else. But essentially, what is lost in potential energy is gained in kinetic energy, and that's a very simple conversion of heat. All right, so we're converting potential to kinetic here. This happens all over the world in all sorts of things. Windmills do it. They take the wind and it moves the windmill and it converts from potential to kinetic. And then, hydroelectric dams, batteries. So these are all examples of things used in your everyday life that use conversions of energy. And this is, I just explained this, so if you kind of got this, you really don't have to write down these two bubble points. As the bicyclist coasts down the hill, her potential energy is converted to kinetic. When she reaches the bottom of the hill, all her potential energy has been completely converted 100% into all kinetic energy. When we start talking about thermodynamics, this law is key. So chapter 5 is focused on thermodynamics. What is thermodynamics? It is kind of the study of energy and energy in systems and surroundings. And the first law for thermodynamics, big one here. Energy is neither created nor destroyed. It's really only changed. Now, if you remember that, we've had plenty of laws where fill in the blank is either created or destroyed, never changed. Mass, momentum. All these things are always conserved in the universe, and thermodynamics is the same. So, what this means is this. Energy is never created or never destroyed. It only changes. So, if we look at the entire universe, the amount of energy in the entire universe is constant. So remember, we talked about there's two things we're going to study, the system and the surroundings. So if the system loses energy, what has to happen? It's gained by the surroundings. If it doesn't do it that way, it lost it somewhere else. But we are only focused on the system and the surroundings. So if the system loses energy, the surroundings gain it, and vice versa. So if the surroundings lost energy, the system would gain energy. That's kind of the general first law of thermodynamics. And when we study this law, we focus on internal energy. And internal energy is the sum of all energies in a system. And we kind of label it E. So the internal energy is labeled E. It's the sum of all energies, and we'll give you an equation for that right here. So, by definition, the change in internal energy is the final energy of the system minus the initial energy of the system. So change in E is equal to E final minus E initial. And remember that you can lose energy or gain energy, so it's possible that the change in energy is negative. Now, changes in internal energy. If the change in energy is greater than 0, if the change in energy is greater than 0, that means the system has absorbed energy from its surroundings. Your change in E would be positive, and that would be called endergonic, which is just, don't worry about endergonic. It's not a word that you're going to worry about. We're going to focus on exothermic and endothermic more importantly. And also, don't worry about getting caught up in these charts. All right, if you want to look at these charts and kind of it helps explain the process, that's fine. Go ahead and do that, but don't get caught up in them. If change in energy is less than 0, that means our change in E is going to be negative. If our change in energy is negative, it's exergonic, which means energy is being released. So if energy is being released, it's negative. If energy is being absorbed, it's positive. Now, when energy is exchanged between the systems and surroundings, as we talked about, it can only be done in one of two ways, through heat or through work. Through heat or through work. That's it. That's the only two ways. So we're studying systems and surroundings, heat and work. So if we put that into an equation, change in E, the change in internal energy, is equal to the sum of heat, which is abbreviated Q, little q, and work, which is abbreviated W. Now, one very, very important thing to note here is this slide. You will want to write this slide down because both work and heat can be negative or positive. So both work and heat can be negative or positive. You'll want to write this down. You'll want to understand this slide. If heat is positive, that means the heat or system. Let me back up. If heat is positive, Q, that means the system gains heat. If heat is negative, Q is negative. That means the system loses heat. If work is positive, that means work is done on the system. If work is negative, that means work is done by the system. So you have two words which are key. If work is done on the system, it's positive. If work is done by the system, it's negative. So something to kind of keep in mind there. And then if change in E is positive, we have a net gain in the system. If change in E is negative, we have a net loss for the system. But this chart you will want to kind of write down and make sure you understand it. Lastly, if heat is absorbed by the system and the surroundings, the process is endothermic. So if heat is absorbed in the system, it's endothermic. And what would it be called if heat is released from the system? If heat is released by the system into the surroundings, the process is exothermic. So just a little bit there. So endothermic, exothermic. So remember, we're studying thermodynamics. There are two things we're going to study: the system and the surroundings. Secondly, we will study what can happen to the system and the surroundings, and that is either work or heat change. That's the only two things that can happen to the system. That gives us eternal energy, which is change in E is equal to Q plus W. And then we look at this slide here to determine whether or not Q and W is positive or negative, and that sets us in the right direction for section 5.1.